Uh, uh,
Hi everybody,
Hello.
how are you? So let us wait for a few minutes so that more people can join. Hi David, how are you?
Can you guys hear me okay? Just want to make sure you can hear me okay.
I can hear you.
Oh, okay. All right. That's good.
I hear you.
I'm
I
having
hear
a,
you.
okay. That's good.
So
Uh,
let us give it maybe 4 more minutes for more people to join.
all
Where
right.
are you, David? Where are you, David? Now?
I'm back at my home in Colorado. So I was going to go in the office today, but doing the presentation from my home.
Excellent. I was in Denver, Colorado, for the ICC conference, and I visited Boulder to meet some people from Nest.
Hey, Hisham, while we wait, can I talk about deconstructing distributed AI with precise time real quick?
Uh, I just want to mention something, and then you can maybe have how much time you need, David. Hi, David. Oh,
David, oh, he's on mute or
I don't know.
no? I can't hear you. No. Looks like he turned mute on.
Hello.
How about now? Can you hear me better?
We
Yeah,
can
I
hear you
hear
better
you.
now. Yeah.
That's good. So, David, how much time you need?
Oh no, if you want to take some time, please, we can, I'll go through my charts fairly quickly and then should have plenty of time for Q&A. So please, yeah, would love to hear what
Okay.
Dan has to say.
Okay, sure. So then you can maybe, do you need 5 minutes or so?
I'll try and do it quick, as like 2 or 3 minutes. Let me share my screen if it lets me.
Excellent. So let
Uh,
me just say something. So this is the second meeting where we discuss quantum communications and try to discuss uh, time synchronization issues with quantum networks and with the objective of trying to build a small team which can look at any issues related to time synchronization and quantum communication. That really is the goal. The August meeting will also be related to quantum communication, and hopefully by the end of the summer, we will form that small team which can be spawned off to do their own research to address this problem. Okay, then now we can have a few minutes to talk about AI
okay.
projects that you are in charge of.
Okay. So we're introducing a crowdsource project. This is under the wiki. We talked about it earlier. Some of us have looked into it and added some stuff to it. There's a presentation and a short video that'll go here when I get a chance to load them. This is the presentation, but the whole idea is to get people interested in looking at how we can deconstruct AI and talk about, we could break it down, for example, physical, logical, security. I'm sure there are many more ways we can break it down. Um, and we've done some of that here. Uh, what we did was we created a document that people can go in and actually edit and talk about how precise time can help, or maybe it doesn't help. And that it's important to know where precise time would be useful in AI and where it's not useful in AI. And so, for example, here we have a um, talk about latency under the physical and talk about QoS and how there might be a way that precise time and QoS could work together for scheduling. Um, down here we talk about math units and how different sizes of your floating point arithmetic or your integer arithmetic could affect your data and how precise time could do it. But we've basically looked at all the different ways that we've thought of, and there are many more. There's only been a few of us that have looked at this so far, and I just wanted to let people know that you know you can get more information. I'll put the video here and the slides here. You can watch it later. This is under our Workstream 10 projects and the crowdsource projects. And that's about all I had. So only about 3 minutes, 4 minutes.
That is good. Thank you, Dan. And I think there was an announcement made by OCP management. We are creating a work stream under OCP, not under OCP tab, for AI. So it's so the whole idea actually is that we look here at different technologies, like Dan talk about AI. We are talking now about quantum communication, quantum computing. These are all interesting topics, and there is more to them than just time synchronization. So it may very well happen that they will create a whole work stream under OCP to address this kind of topics. But for now, in this kind of this work streams, time synchronization, industry and academia engagement work stream, we are focusing only on time synchronization. I would like to introduce our speaker today, David Mittling. He is the CEO of Kairos, with 3 decades of experience in the space and photonics industry, including huge space and communications, orbital, Maxar, Ragecom, and SP Quadral. David has a BS, Bachelor in Aeronautical Engineering from Cal Poly, SLO, a Master in Aeronautics and Astronautics from Stanford University, and an MBA from MIT Sloan School of Management. Oh man, you have many degrees, David. You are a very smart guy. Please, the floor is yours and go for it.
All right, thank you so much, Nathan. Really wonderful. I appreciate the opportunity to present because I learn a lot from this group. So it's just wonderful to be part of this working group and OCP and Time Appliance Project and this working group. So let me go ahead and bring some charts up. Ping me if you cannot see them. They should be up by now. So this ties well, I think, with the conversation we had last week with Tara, who talked about quantum networking and the impressive work they're doing at NIST around quantum networking. Because what we're doing at Zyros is leveraging existing entangled photon hardware for kind of a novel and interesting way to do very secure and very accurate time transfer, what we call quantum time transfer. This is based on a protocol that my co-founders, brilliant quantum scientists, invented in 2018. It was demonstrated in a quantum lab in Singapore in 2018, generated a few more papers, a patent, and we formed our company around this in 2019 with the idea that this is an opportunity to commercialize this novel technology. It leverages hardware that's already out there. It's been developed and built and being installed in networks for an application called quantum key distribution and quantum networking. So it's nice because it plays in well with what's being developed by Tara and the people at NIST and elsewhere. And we look at this as potentially being a part of a kind of a future time transfer, time synchronization, and PNT network, augmenting the networks and systems out there, which is part of the reason we want to engage with this community to understand how this could work. So after last week's presentation, I thought it'd be fun just to start with a high-level description of, what is quantum, what isn't quantum. There's a lot of hype out there. Right now, we're in the midst of what they call the second quantum revolution. We're kind of leveraging the ability to manipulate the quantum properties of small particles based off theorems that were only created like about 100 years ago. So think about these things were 100 years ago, this was brand new. You think about Niels Bohr and Einstein and all these giants of the quantum community. These were thoughts, experiments, and papers that led to experiments. These experiments led to lasers and semiconductors, atomic clocks, MRIs, that led to the first quantum revolution in the 50s and 60s, that created these huge benefits for society. The fundamental difference today is now we're actually manipulating the quantum properties of individual particles for very impressive applications. And the reason that you're doing that, like you're kind of leveraging a few kind of quantum capabilities. The biggest one is, if you guys remember from your quantum 101 class years ago, everything that has kind of a quantum state, a small particle that's in a quantum state, you only have the ability. It's a superposition of multiple kind of multiple states until you observe or measure it, and then it collapses. The wave function collapses, and then you can only kind of collapses to one polarization, one momentum, one position, one spin. And that actually creates an inherent level of security because you can only measure or observe a particle once before it collapses, and that lends to the no cloning theorem. So a lot of the technology that we're using has that security associated with the fact that you can only observe or measure these quantum states once. Now, the other obviously major quantum property mechanics that has enabled this second quantum revolution is entanglement, this so-called spooky action at a distance. Entanglement is interesting because it came about as part of the APR thought experiment in 1933, created a lot of waves in the brand new quantum community. And today we're actually leveraging these kind of quantum capabilities. The idea that if you have two particles that are entangled, they share the same information, they share the same state. And when you measure, observe one, the other one collapses instantaneously, and you have that entanglement. And again, that creates kind of a level of capability and security because, again, no outside observer other than the primary parties can measure it and see what's going on behind the scenes. So now you all kind of caught up. We're all back to the world of the reality. This has kind of created a whole industry of quantum technologies that really fall into three major baskets: quantum computing, quantum communications, and quantum sensing. Now, quantum computing is what everybody thinks of when they think of quantum. This ability to kind of use entangled particles, in a stationary state for some amazing kind of processing and optimization, solve optimization and algorithms that a classical computer or the best supercomputers in the world would take thousands of years to solve. So that gets all the funding, that's get all the interest, but I would argue this is the system or technology that's probably the longest away from having real, true commercial applications. Though you're starting to see some major breakthroughs in the news recently on quantum computing. The other one that's out there, just incredibly disruptive capabilities, is quantum sensing. So these are basically using typically what they call cold atoms to do very accurate inertial magnetic field, gravity gradient field, RF sensors that could be, again, very disruptive in the future. And kind of under the umbrella of quantum sensing, you have these atomic clocks, which include the great work of companies like Inflection and groups like that are doing these optical lattice clocks, just in very, very impressive things. But that's not where we lie. That's not where quantum time transfer resides. We are in the world of photons, entangled photons, flying qubits. Quantum communications is probably the least well-known or famous, but it's the most commercially viable. There are systems being installed today in networks around the world, primarily for an application they call quantum key distribution. This idea that you're using kind of entangled photons or photons in a quantum state to very securely and very accurately distribute encryption keys. But there's the other major kind of application is quantum random number generators. There are a whole series of Samsung phones that have QR and G chips in them, being built by a company out of Australia and Korea. So when I say these are commercially viable, I mean, you could buy them today, you can install them, you can play with them, you can send entangled photons flying across your fiber networks across the room today. These are off-the-shelf items. Now, we had the nice presentation last week from Tara talking about quantum networking. I'm going to talk about this application, which is using it for transferring time. And so just again, to kind of reiterate, when people think of what we're doing, they think we're quantum computers or atomic clocks or these incredible, quantum sensors that can figure out your position navigation. No, we are not. We are entangled photons. So it's just want to be very upfront about that. So the way that all quantum communications work is you start with an optical system. You're all familiar with optical systems. I mean, if you have a laser, you pulse it on and off, you're sending zeros and ones for high rate data. That's over fiber. That's been around forever. With quantum communications, you're actually dialing the power down. So you get a small stream of photons, and then those individual photons are converted into pairs of photons that are entangled. This is what they call an entangled photon source. And there's a few different ways to create entangled photons. What we primarily use is what they call spontaneous barometric down conversion, where you shine a blue laser into some very carefully cut nonlinear crystals, that convert individual blue photons into pairs of red photons that are entangled. And the output of this source are two photons. They're entangled, and one goes one way, one goes the other, is signal idler. And the value of this is you can send one to one party. In classical cryptography parlance, that's Alice, and you send the other one to the other party, that's Bob. They have a detector, a single photon detector that detects each individual photon. And because of the magic of entanglement, if Alice measures a 0, Bob has a 0. And they can use that to create a truly random string of bits that they share, only they have. And if a man in the middle, Eve, an eavesdropper, intercepts a photon meant for Bob, both Alice and Bob would know it. Again, the no cloning theorem, you can only measure it once, entanglement's broken. So this was created, invented in a protocol going back to 1991, the E91 protocol. And so these products are being developed and being built and installed in networks as we speak. They're being put on satellites. They're being installed on fiber networks. Very capable systems and off the shelf. The breakthrough that my co-founders had was, hey, Alice and Bob have clocks, and Bob wants to synchronize his clock to Alice's reference clock. So this is using this hardware and systems developed for quantum key distribution, but for time transfer. And you guys are all familiar with time transfer. This is the meat and potatoes of what we're doing within our group. So when they developed this, they started, they wrote a paper on this in 2018. They kind of built on some papers that were going back to 2000, late 2010 timeframe, developed by John Dowling and some other giants within the quantum industry. But they developed what was the original quantum time transfer two-way protocol in that paper, demonstrating that lab in Singapore, and we've been, it's been working great ever since. Those original demonstrations, we got down to 50 picosecond precision, synchronizing Bob's clock to Alice's clock, and we are, so it's, now since then, a number of groups, including us, have developed our own follow-on systems, and now we're kind of picosecond, sub-picosecond capability. And as I'll explain a little bit, with the hardware improvements, we could get to sub-picosecond precision, but we're kind of arguing amongst ourselves who really wants that level of capability. And funnily, the way it works is, again, you're kind of starting with, the source of entangled photons. Bob and Alice, a pair of photons are created. They have a very tight time correlation at the time of creation. Alice measures, one goes to Alice's single photon detector. It's detected. It's stamped with her clock. So she has a time reference for that time, that photon. The other one goes to Bob. Bob, same kind of thing. Bob stamps it with his clock. And then you have a classical communication link between them. You get a number of photons that make it to Bob, and they do like a classical communication comparison, and they find that offset from the cross correlation peak between Alice's correlated events, Bob's events that are correlated to Alice's time detected events. And here's the gory math. You can go back to the paper and look at it. We actually had a project a few years ago that led to a demonstration of free space quantum time transfer demonstration by Air Force Research Labs. These diagrams here come from their paper, so I'll give them credit for it. But it kind of visually lets you kind of see how it works. A small fraction of the photons created at Alice's source, make it to Bob. But what we're finding is the system is very robust to link loss and background noise to extract that cross correlation peak or that correlation peak. So one of the benefits we're finding from this is its ability to work in kind of over long distances, which is kind of why we're looking at some interesting applications associated with that. But again, you only need a small fraction, 45 dB loss or potentially more. You can still extract down to the picosecond level precision that offset between Alice's clock and Bob's clock. And of course, the more photons you get, the better the precision, but the better your capability to slice this into time bins and get synchronization, kind of calculate the frequency drift offset between Alice and Bob. So we've demonstrated this in a lab. We've now demonstrated in our own kind of what we call proof of concept. So what's the point? I mean, how can we use it? What's the value of it? So we kind of honed in on a couple of potential system use cases and system architectures, kind of starting at a design that would host this on a satellite and provide timing distribution over a large area as something that would augment the timing that we get from a GNSS system like GPS. And you guys are all familiar with this, you know, both RF time transfer, GPS, in particular, that diagram. Um, it's a one-way RF time transfer where you're using biphase modulation and encoding information about the satellite with that biphase modulation. So you kind of create these codes or kind of chips so that the satellite transmits information as well as kind of the timing offset. The receiver knows that those chips are that kind of PRC pseudo-random code and can kind of use that offset to figure out the time or the distance of the satellite. And that's how the receiver resolves its position and time from a series of GPS satellites in view. Fundamentally, we're just looking at time. We're starting off with very basic. I only care about time transfer. So if you have a common view of a satellite that we have, then we're only looking at the time transfer. And now you're using individual detection events from photons rather than kind of the change in phase that you get with a very stable L1 type signal from a GPS satellite. So it's just a fundamentally similar type time transfer, but we're using direct detection events rather than change in phase. So we started with that. We kind of started with that as a baseline to say, okay, what's the value of this versus an RF time transfer type system? We built a proof of concept. We did a kind of free space and fiber links between Alice and Bob. With that, we created a simulation model. And with that simulation model, we have a fairly good confidence that we can achieve a system design that gets us to 10 picosecond or better precision, even with kind of the natural atmospheric losses or issues that you have with the satellite to ground link. We also then get the benefit of the resilience and security that you get with tangled photons. So the nominal value that we see is really in the security and the resilience. And so if you look at why, kind of how that resilience comes about, again, this goes back to that discussion we had about, you know, just the quantum theorems. The quantum capabilities are the foundation for the distribution of quantum encryption keys called quantum key distribution. These are based off of papers and proofs that go back, you know, 3 decades. These papers have been subject to very extensive security proofs and scrutinization within the security community. So when we're looking at this, we see a value that for groups that really need what we call authenticated time, the ability to say, I trust that timing source, that kind of grandmaster or reference clock is something that's not coming from an adversary, and it's not being spoofed, it's not being jammed, which is a fundamental problem that you run into with GPS or other GNSS systems. I was at a presentation about a month ago at the European Navigation Conference, great presentation talking about lessons learned from what's going on in Ukraine, and how spoofing, this ability to, for an adversary that used to be very sophisticated, to make you think you're in a different position or time than where you actually are, it's now becoming very commonplace and very easy. Jamming is very well known. You know, you just turn up an RF signal nearby and you're overwhelmed their receiver, and you know, you basically just lose all your position and timing reference. But spoofing is very insidious because you don't know what's happening. And with new advancements in software-defined radios and phased array beamforming kind of antennas, it's become trivially easy to build and develop this at very high levels of sophistication. Now with our system, we have those that capability to authenticate and prove that the time is coming from your source and your source only. Just there's no way that you could spoof it. If somebody can figure that out, they're going to get a Nobel Prize because it's just fundamentally impossible to kind of measure or retransmit those photons. And it's because if you want to dig more into that, happy to give you more information. But you know, it's based on Bell's inequality and the no cloning theorem that kind of creates that basis. The other thing that we're finding too, and this is really what we're finding out from kind of experiments more than anything else, is just how resilient this is to detector noise and link losses. One of the things I think that kind of limits the floor for you know, some of these other systems is not only you have a weak signal coming from a satellite that's 20,000 kilometers up, but also just, you know, you got some things that kind of provide kind of degrade the performance, particularly the farther away the source of the timing signal. And then the other thing which has some value, not for the commercial community, but for kind of military applications, is the fact that you're dealing with entangled photons at such a low power level. I mean, they're picowatts or less. So an adversary can't detect the source. So even knowing, you know, where it's at and jamming it is nigh impossible. This is what they call LPI, LPD, low probability intercept, low probability detection. And it's a very directional beam. So if somebody wanted to try to mess with that signal, they would have to be directly in between, say, the spacecraft and the ground. Now, accuracy and precision, that's also another kind of area we're looking at. Again, we're trying to understand from the community who really needs sub-nanosecond. Tara had a great presentation, I thought, last time, and she talked about their need for getting down to picosecond level precision for quantum networking. Now, quantum networking, I'll got a chart on that later, but quantum networking is this interesting out the door application, not only because it's the really first need for picosecond level, but B, it also leverages the same hardware we're already using. So we can piggyback off existing designs to do the time transfer to that precision in addition to the quantum networking. So the accuracy really comes from the fact that you're doing a direct detection rather than trying to parse out you know, the difference in a pulse or a phase. Or I know there's some new things coming out, kind of Doppler things that you could do to try to more accurately, you know, pull out the time transfer signal. But you're dealing with you know, you're time stamping individual detection events. You also have a very accurate correlation of the creation of the entangled photons, roughly, you know, sub kind of femtosecond level. And in theory, we could achieve precision down to 40 femtoseconds on paper with existing SPDC sources. We're dealing with individual photons, so you don't have kind of the change in the waveform, you know, associated with an RF or an optical pulse. Especially over long distances going through atmosphere, those dispersive effects, your nice crisp, you know, waves or pulses, you know, kind of get distorted over, you know, across a thing. We're not dealing with it. These are individual photons. So when you look at the errors associated with a GNSS type system, we can really do a lot to overcome the losses due to the atmosphere, multipath because it's very directional. And the receiver noise, we have our own kind of noise associated with the single photon detector, and I'll mention that in a minute. But we're not doing an ADD, you know, A to D analog to digital converter. You don't have that quantization error. You don't have kind of those losses with our system. So that also brings another interesting thing that we've been looking at, and other groups have been looking at too, is, you know, you could also look at an optical time transfer system, especially if you have a space-based system that has an optical comms link on it. You know, you just basically kind of have a modulated optical beacon. And the value of an optical time transfer versus quantum time transfer is just, again, a lot of the same value, the directionality, the accuracy and precision that you would get. Plus, you can kind of leverage existing optical communication systems. So this is something we're looking at as something that we would work with and kind of maybe develop in parallel with a quantum time transfer system. However, there are some benefits that you get with using entangled photons rather than the sharp pulses with these ultra-fast pulsed lasers. So a little background on optical time transfer. One of the things that people have to understand too is we've been talking to a lot of companies and partners, but really there's not a lot of groups that have looked at kind of practical optical time transfer in the space domain. Now, in fiber, that's a different story. So White Rabbit is a protocol that was developed at CERN. It's been around a while. There's a few companies commercializing these systems for fiber-based systems. They're getting sub-nanosecond down to picosecond level regime. Very good quality companies that include Seven Solutions that got acquired by Safran, OP&T, other kind of impressive companies that are doing very well selling this into fiber networks. And I know when I talk to the groups that are doing quantum networking installations, they really love their White Rabbit products. Just work very well over fiber-based systems. And I think some financial networks and some other kind of applications are looking at that too. But in the space-based regime, there's only been experiments. And we're working with some of the groups that have been doing this. So satellite laser ranging has been around forever. This idea of using, there's satellite laser ranging stations around the world. NASA hosts them. Then they're using them not really to distribute time, but to figure out very accurately the distance between satellites for satellites that are kind of being used for orbit determination and maybe metrology, not metrology, but kind of instrumentation type of things. Using kind of the laser pulses and just those offsets to figure out the distance between satellites and the ground as it passes over. There's been some experiments done on the Jason 2 satellite. There's a satellite that should be launching soon with some out of MIT and NASA called the CubeSat Laser Infrared Crosslink that's going to do a optical time transfer between satellites. But the most interesting is really these optical comb developments. And we've talked to some groups, particularly Nate Newberry and Laura Sinclair's group out of NIST. They are doing some very impressive things with optical comb. I think we've had a presentation here. I'm not going to go into it because I understand the basics of it, but optical comb technology is very useful, particularly for like synchronizing clocks and relatively close proximity. Because you got that nice optical to microwave interface regime kind of thing. And then there's companies like Vescent and a company we've been talking to recently, Longpath Technologies, that are using these advancements with optical combs, not just for time transfer, but also like Longpath's case, they're actually using it for spectroscopy type applications. Because if you use this in a free space environment, you can also use that to find elements, greenhouse gases, and pipe leaks and things of that nature. So very impressive stuff that they're doing, and they're benefiting from these advancements going on with the combs. The free space demonstrations they've done at NIST have been really impressive. They've been doing across 2 mountaintops in Hawaii. If you go out to their facilities on Boulder, you can see them do both optical normal beacon time transfer and comb just bouncing off a retroflector in the mountains off their facilities there. And they're also working toward a space-based mission that was, at least last I heard, was called the Optical Clock Orbiting in Space, FOCOS mission. So very impressive stuff. So we're as a company, we're still looking at the trade space between optical and quantum communications. But quantum has some long-term capabilities that really are appealing to us. Again, even the optical system has quite a bit of security built into it. But, again, you just don't get that level of security. For the truly paranoid, maybe the kind of the military and groups like that, there's a quantum system is really just kind of the highest level of security. Again, the fact that it's being implemented for distributing encryption keys, distributing time is such a lower security, kind of capability today. So we can very readily just provide something that's much, much more secure. But we're also seeing a kind of a long-term benefit with the development of the hardware. So like I said, we're leveraging quite a bit the fact that there are off-the-shelf systems. Everything that we built with our proof of concept was developed using things that we could buy that were less than 20K a box, that could be procured and assembled very rapidly. When we built our proof of concept, we kicked off, we went out to the vendors and we had it built and running within a month. Just nice because you're not need to develop a whole bunch of new development that you would have with some of these other kind of optical time transfer systems. The other kind of value that you get by going with a quantum-based time transfer system is that these kind of what I consider the add-ons, the tack-ons. For example, if you have a system, a space-based system that's providing time distribution, authenticated time, you're also could offer delivery of encryption keys as a free add-on and an optical communications link. So now within your network, you can have a kind of an optical backup as well as an optical comms backup as well as providing encryption keys with essentially the same hardware suite, that ground receiver. There's also kind of some long-term value that we're developing. And this is years out, maybe even decades out, where we can leverage what they call like some new paradigms with network security. So this is probably well known within this community, but if you have very accurately synchronized nodes down to the sub-nanosecond, picosecond level accuracy, now all of a sudden you can look at time of flight to do sensing within your network. The time of flight will tell you kind of just, well, for example, over fiber, if you know that to a relatively decent accuracy, you can actually see the temperature variation of the fiber over the course of a day. But if you take it to a step further, you could also use this to, say, detect a network intrusion. Now, DARPA and some other agencies have really been interested recently in looking at quantum entangled photons and kind of these quantum effects to detect network intrusions, different types of network intrusion into fiber networks, because they really want to try to go to the physical layer rather than the software layer, the cybersecurity layer, to detect, kind of issues or kind of physical intrusions tapping into fiber networks or other kinds of networks. So this is one of those things where there's some future development there, but again, it has that additional network security that can tell you whether there's some implications there. The other part of that too is the sensing applications. So if you're sending entangled photons, either free space, let's say you're sending free space, across multiple towers or over fiber or even satellite, the dispersion effects, if you go to different wavelength photons, you can use that relative time, time of flight between the different color photons to tell you about, say, moisture in the atmosphere and other kind of effects like that. So now all of a sudden you can use, by having a transfer and receiver between two nodes, you can tell what's going on in between those two nodes. And then of course there's the quantum networking. So, quantum networking works really because it's the reason you need that sub-nanosecond accuracy is because in that case, you have a source here. You have three nodes. You have a source at node 1, you have a source at node 2, and you're trying to get a photon, a coincident photon at the middle node, node 2, at the exact same time within a very tight time correlation, which means you got to know to very accurate synchronization when to send those photons because you want those photons to arrive at the exact same time at that middle node to get quantum teleportation, which is that step toward quantum networking. Which is, if you look at Tara's presentation, that's really what it boils down to is you're trying to get those photons arriving at the exact same time. It's very, very impressive stuff they're trying to do, but much harder than what we're trying to do as a company. Now, the other value of quantum time transfer, again, we're looking at optical time transfer and quantum time transfer. We're looking at putting these on satellites. We've gotten some projects in development to get us there. But one of the things that we're finding is, there's a common problem that you have for optical communications, optical time transfer, and quantum time transfer. Um, it's essentially piggybacking off the same designs and the same systems. So you have a lot of the similar problems. The obvious one is the link budget. So if you're working in an optical domain, our hardware we built is at 810 nanometer wavelength. Most optical communication systems are at 1550 nanometer, which is kind of the near infrared wavelength. 810 is, kind of in the color spectrum, but very low power. Now you got to look at just your losses through the atmosphere. That's a huge problem when it comes to optical communication systems. You're trying to have kind of a coherent phase, pulsed communication system going through the atmosphere. So scintillation effects and those kind of things are a killer for you when it comes to optical communications. But when you're dealing with individual photons, and we're only trying to get a few hundred photons per second to the ground and to the ground receivers, we're less sensitive to those kind of things. But the link budget is something you have to deal with, either optical or a quantum receiver. So you want a bright source, you want a fairly large aperture to get more photons to the ground so you can get that precision necessary to make the system work. You also have to have a fairly high pointing and tracking accuracy on this. You have to account for Doppler effects, especially if you want to get sub-nanosecond level accuracy, relativistic effects, impacting the clocks on the satellite. Because a two-way time transfer system requires an assumption of reciprocity, the equal distance on the up and down link. You have to account for that with what they call the point-ahead angle, which means you have a good understanding of the difference between the transmit and the downlink and uplink time of travel. Doppler effects you can overcome by having an a priori knowledge of the range rate, the change in distance. Having a priori information on that will help you correct for Doppler effects. And then, of course, you want to have hardware that fits on satellites. And that's because we're looking at an architecture where our system would be, hosted on a satellite, a geosynchronous satellite or a MEO satellite that sits as a clock in the sky. And it would get its time from a local time reference, say the NIST clock here in Boulder, the Naval Observatory, or any one of these kind of timing references that are really accurately tied to UTC. And then that clock sits there, and that becomes the kind of reference time in the sky. You could use that to synchronize the satellites in a constellation. So if you have satellites in a LEO, MEO orbit, or even a GEO orbit, then all those satellites would be tied to each other with a quantum link. So you have a synchronized constellation, which has value for kind of a global time distribution architecture, as well as satellites that are in formation flying. We're finding that's a very interesting use case, particularly for using these satellites in sensing applications where you're kind of treating them as like multiple elements within an array. But the larger architecture, if we're looking at where this could fit in a future system, working with companies here in the Time of Flies project and just kind of a long-term vision, is having our system hosted on other people's satellites that provide that timing reference in the sky to augment GPS and other GNSS systems, that provides time distribution, a timing reference within nodes within a large network that is in common view with the satellite. And then that provides timing references, distributed across all of North America for a satellite that's over North America. And then, of course, the time distribution goes out from there, kind of acting as a grandmaster reference as nodes within that network over the traditional time transfer systems, using NTP, PTP, White Rabbit, and so forth. So this diagram here is taken from what they call a super GPS architecture. This was based on a paper that came out of TU Delft, and now we're working a bit with TU Delft on the next iteration of their super GPS architecture. It's a brilliant design. A lot of companies are working on this. This idea of using the cell towers in urban areas to provide that last mile PNT. But those cell towers and base stations need to be very accurately synchronized. If you want to get, a link, if you want to get that position accuracy to your phone down within 10 centimeters down to a centimeter, you really need that accurate synchronization within the network. And you're not going to get there with the GNSS type timing reference within your architecture. Now, the other kind of value that we've seen is just, again, that resilience to link loss. That led to a paper that we generated with NASA and JPL, looking at quantum time transfer for deep space missions, and a study that we did with NASA looking at for cislunar links. The realization we have from all that is it does work well for that. So there's a lot of interest now in what they call lunar PNT. And we have these kind of concepts where we use a quantum time transfer for timing distribution on top of an optical layer that provides communications and even power beaming, so that within this kind of lunar infrastructure, you imagine like kind of mining and exploration vehicles, autonomous, running around in a crater, mining ice and doing these other things, but they're in the dark, they don't have any sun. They're getting their timing and communications from systems or kind of base stations at the ridge of the crater that have access to the sun, that provide the not only the power provides the power, communications, and PNT links to them with an optical setup. So real quick, I'll go through this, but we're kind of leveraging hardware that's relatively off the shelf. This is a little cheesy video of our proof of concept. Our proof of concept consists of the entangled photon source. This is just a fairly basic Thorlabs source that we bought. It's very low power, about 100K, 100,000 pairs produced per second kind of thing. A pair of detectors at Alice, a pair of detectors at Bob. And we have both a free space and an optical connection, or a free space and a fiber connection between Alice and Bob. The key development for making this work with any kind of system is the source and the detector. So the sources are off the shelf. We got a nice partnership with one of the major source providers, well, with the source and detector provider. Again, these are SPDC sources, and what we built and demonstrated at picosecond level accuracy leverages a source that's about 100,000 pairs per second. The state of the art today is couple mil pairs per second. So quite a bit brighter. That's the brightness of the source, is the output of the power of the output of the pairs. And there's a roadmap to get to 10 million, up to 1 billion pairs per second on something that could be hosted on a satellite. So very bright sources. And you can do the math yourself. We're only trying to get a few hundred photons per second to the detector at Bob. So, you can figure if we have a source that's producing 10 million pairs, you only need to get a few hundred. We're very resilient to link losses. And what we see in the proof of concept, which we correlated to a simulation model, is that assumes a very noisy background. So the detectors we use are kind of just very cheap off-the-shelf silicon single photon avalanche detectors. They are optimized in the 800 nanometer regime. They're noisy. They have what they call dark counts, which are kind of false counts that pop in there. And plus they have what they call efficiency. So if you have a detector that's at 60% efficiency, that means 60% of the photons that arrive to it get detected. The others aren't shown as an output. But one of the things that we've seen with our system where we could actually get even better precision is with the timing jitter. So every time a photon hits a detector, you'll time tag it within a window, and that window is typically kind of dictated by the timing jitter, or I should say the pulses output within that window of the timing jitter, which for silicon SPAD is roughly 400 picoseconds. The state of the art today are what they call superconducting nanowire single photon detectors. They're very efficient. They're in the 90–95% efficient. Very low dark count, so they don't get those kind of false outputs, which kind of they're kind of analogous in my mind to thermal noise in a GPS receiver, for example. And you get, but the thing that really excites us is the timing jitter is closer to 5 to 15 picoseconds. And with that, we can actually really start to improve the capability and the precision and start looking at low digit picosecond, sub picosecond level precision. The negative with these superconducting nanowire SPDs is SNSPDs is that they have to be cryocooled down to, so many millikelvin. And so the hardware is a couple orders of magnitude much more expensive, and you have to have cryostats and all these kind of things. But that technology is moving along pretty rapidly. So I think for some ground receivers and particularly even some kind of free space or space fiber-based systems, that's something that we have in our technology roadmap, particularly for groups that really want to get down to that low precision, which include the quantum networking applications where they're already using, these kind of fiber-based systems within a controlled environment. I'm not going to say cost is no object, but they're a little less cost sensitive. The other thing that we're benefiting from is just there has been a ton of development in the last decade or two on free space optical systems. So these are third-party designs. My understanding is SpaceX is the leader in this now, and they're actually selling their free space optical communication system on the open market now. All right, I think I'm pretty much wrapped up here. Here's a nice little block diagram showing you how it all works and as it ties into our proof of concept. Fairly straightforward. You're just sending photons between point A to point B, Alice and Bob. Our plan as a company now, so we built the proof of concept, 2 nodes. We now got some contracts where we're developing free space, space-based, and ground terminals with these contracts and with these announcements out in the next couple months. But our goal as a company is to get this on a satellite and show this that it works. That's the key step to getting to something that's a practical global time distribution system accurate to 10 picoseconds globally. Now, we're not the only company that's done this. We've worked with a few other groups, including the Air Force Research Labs. They have a couple papers that were published last year talking about their demonstration of free space optical link, free space quantum time transfer at their facilities in Kirtland and Albuquerque. But one of the things we've seen is that when our original papers were published, other groups took them and they're doing some very advanced development with them, including China. So I'd be remiss if I mentioned that they are, I have to say, the leader in this space because they've now done this. They're installing it under fiber networks. And last October, they announced they're launching this on their next set of quantum satellites that are going to orbit probably in the next 2 years. So they're going to MEO and GEO orbit, and they're going to do quantum time distribution over fiber and space-based systems at that time. So with that, I think I got a few minutes left over. Let me open the door to questions. I don't know. Hopefully it was all clear to everybody.
This is an excellent presentation, David. Really.
Thank you.
Very good. So, any question from anybody? I have a few questions.
I think Kent has a question.
Yeah.
Oh, no, so I was just doing the clap. I think that was awesome. Very, very good.
Yeah, it's a great presentation. So, if nobody has a question, I have a few questions. Question number 1, David, is it sounds like based on slide number 33, you can use quantum time transfer to synchronize satellites, synchronize time between satellites, right?
Correct.
Oh, great. Because if you remember, I have been looking into this time synchronization between satellites. And now you are solving the problem using quantum time transfer. That is novel. Because everybody I talk to, they tell me they use NTP and BTP to do that. Now you are doing something novel.
Yes. No, that is almost an ideal use case for us. So we had a contract with the Air Force where we looked at synchronized constellations. And I don't know why the Air Force is interested in this, but they were very interested in this. So yeah, that is actually a very good use case for us. And now we're looking at other applications where we have satellites in formation flying, particularly for these kind of scientific experiments. I think probably the same thing you're looking at, Hesham, which is this ability that when you have satellites in formation flying, you can use it like Grace and Grail, which were used to kind of measure the gravity gradient as it was flying around the moon and flying around the Earth. But also, those synchronized satellites with sensors on them could be used to detect gravity waves and some very interesting sensing applications where you really want the distributed sensors.
Excellent. I
Yeah.
like this. I
Yeah.
like it. Can you please just quickly, Dave, summarize the challenging problems that for time synchronization in quantum communication that you would like the team to work on? Just a quick summary.
No, I would love to have, partners on the space side of things. We got some good partners on the quantum side of things, but again, interfacing to clocks, using this, I think to, having that kind of developing this with clocks and clock ensemble. We're really now at the point as a company where we're trying to do multiple nodes, interfacing to kind of off-the-shelf clock systems, and then understanding, kind of where the use cases, the needs are. That's why I like Dan. Dan, you started off talking about, hey, you guys are looking at synchronization needs for AI and data centers. That is a very interesting project that we would love to develop with you, just to understand where your needs are. But again, that's why we're part of this working group, is just to get to understand what the needs are, and we can solve these things. But yeah.
What you are saying, even in AI, the data center, we can use your technology for time synchronization.
Yeah,
right?
I believe so, but I'm learning. So, we don't want to put a round peg in a square hole, but we're at that stage as a company where we're looking for partners and we're looking to understand, where the development needs to go.
Excellent.
Oh, sorry, Hisham.
Yeah.
How expensive is your equipment?
So the proof of concept you saw there, again, it's kind of ratty, but it was, $70K all in bill of materials. Seems a bit high, but one of the things that we're trying to develop is there's some really impressive things going on with entanglement on a chip. So everything you see here, kind of on the like say on the left-hand side, will eventually, like over here, all of this will eventually be on a card. So we are kind of trying to look at, okay, how do we get this down to the point where it's, near term, we're trying to get sub 50K, but down to, 10K or less for a card that could be installed at quantity. Now, you guys tell me, is that ridiculous, or is that just the non-starter? But I feel like this isn't going to replace NTP or PTP or anything that you're already used to using. But within the network, it can provide kind of a reference node for the distribution of timeout from there.
Right. So like one a rack, at 5 to 10K would probably be acceptable, but one per server or something like that, that would be probably doubling the cost of the server.
Yeah. Yeah. No, and that's like the direction feedback we want to do, because we want to get to, an architecture that makes sense and a price point that makes sense.
Thank you.
But yeah, a simple question, David. When we have a quantum communication network, why don't we use PTP, for example, for time transfer?
No, that's a great point. Again, the value of one of the things that with quantum networking, you look at what Tara presented last week, they're already leveraging all this hardware. This hardware that you're seeing there is already in the quantum network. So in our mind, we can kind of just use it for time transfer for free. But NTP and PTP, I think, is kind of what they're using. They're definitely doing leveraging a lot of White Rabbit type products, because they do need to get that picosecond level accuracy. Again, because they're trying to get two sources to get a photon to arrive at a coincident point at the exact same time within a picosecond or a few picoseconds. And you imagine the further away those two nodes are from the center point, the harder that's going to be. I mean, that's really, really a challenge. You can do it in a room, where, but what they want to do is the quantum networking over 100 kilometers. So getting that photon to arrive consistently at the same point, that's That's what's going to be a bit of a challenge. So maybe PTP will get them that synchronization, that level of accuracy they need, but they're struggling with it.
Good. So when I met Tara in Nest in Colorado a couple of weeks ago, one of the issues she raised is how we can line up or align the work in classical computers and quantum computers, right? Because
Yes.
I am going to chair a panel in Dubai, and you are welcome to join the panel. And one of the issues she wanted to discuss in the panel is that lineup between the two. And because there are some issues there. One of them is what you just mentioned about PTP, for example. I have the card there already for quantum. Why don't I use it? You know?
Yes.
So these are important issues. I think you are raising very interesting stuff, David. I really like your presentation. Really.
Yeah, no, thank you. And I appreciate again just the chance to be part of this working group and being part of this. And so I'm happy people, if they have questions, yeah, please ping me, because love to have these more detailed discussions. Again, we're at that mode where we really want to learn from you and the community.
I'm learning from you, for myself. So I think, Dave, you, Tara, and other people I met in Nest when I visited them can really formulate a team in addition to anybody who's attending this call to address some of the challenging problem you mentioned in your presentation. I'm sure Tara, she's going to France. She has an assignment there, but by and large, she will have enough time. And I have other people in Nest too who are willing to work with you to address some of these challenges. And I hope people attending this meeting will have the time and interest to join that team. It is really an area for excellent research, seriously.
No, I agree 100%. I was her presentation, because I had never worked with her or her group. We worked with a couple other groups, but yeah, I'd love to be involved, and definitely I'm looking to get more engaged with their group.
I will connect you with those guys in Nest.
Please.
That I met can work together, and anybody who is attending, who is interested to join the research to address many interesting issues in quantum communication and time synchronization, please send an email to the group, and we'll hook you with that team. The tons of paper we can generate out of this.
Yes, I agree.
Yeah.
I agree. Yeah,
thank you.
Thank you.
No, go ahead.
No, I was just going to say again, appreciate this opportunity, and where every time we have kind of these discussions and meeting, it inspires new ideas too. So we appreciate that.
Exactly. And next month's call will also be in area of quantum communication. I'm going to bring somebody from Nest again to talk more about it. And hopefully by the end of the summer, we can form a small team to tackle these issues.
That would be great.
Yeah. Thank you very, very much. And thanks to everybody for attending. Have a great week and take care.
Thanks, David. Thanks, everyone. Bye-bye.